Welcome back to another lesson related to trigonometry. Today we continue our discussion about the incenter and incircle of a triangle. We've already seen the circumcenter and shown how that is related to the law of sines. By the end of this video, we will see how the incenter is related to the law of cosines. Stick around for that. Let's begin our discussion with this dodecagon. Dodecagon because it has 12 sides. This is a regular polygon because all the side lengths are equal to each other and all the angles are equal to each other as well. Now if I were to unravel the polygon, you'd see that a number of identical isosceles triangles form. In this case, there are 12 isosceles triangles because we started with a 12-sided polygon. If this represents my isosceles triangle, we know that the area is equal to 1/2 the base times the height. We also know that there are, in this case, 12 triangles from the dodecagon. So if I multiply this by 12 and rearrange the terms a bit, I will get area is equal to 1/2 the height times 12 times the base, as seen here. We know that 12 times the base is the same as the perimeter of the original dodecagon. So I'm going to rewrite that as P for perimeter. Now I'm going to introduce this small letter A called the apothem, which is the same as the height of this isosceles triangle. And in the case of a regular polygon with an even number of sides, the apothem is effectively half the height of that polygon. So in summary, the area of a polygon is equal to 1/2 the apothem times the perimeter. Now be careful, this only applies to regular polygons, as we'll see in a moment with some counterexamples. But before we get there, let's explore one interesting thing. What if instead I flipped one set of those triangles upside down and fit it into the other set, as seen here? Now I effectively have a parallelogram. We know that the area of a parallelogram is the base times the height. In this case, the base is half the perimeter of the original polygon, and the height is the apothem. And we'd come up with the same expression for area. Consider the limiting case. If we think of a circle as a regular polygon with an infinite number of sides, then these isosceles triangles become infinitesimally skinny, and the parallelogram approaches the shape of a rectangle. Using that reasoning, we can show that the area of a circle is equal to pi r squared. Moving on from the dodecagon to the hexagon, we know that a regular hexagon can be split up into 6 different equilateral triangles and unfolded in a similar fashion as we did before to get the expression for area. But what would happen if I were to smash that hexagon a bit and flatten it out? It still has the same side lengths on all 6 sides, but it no longer has the same angle at each vertex. In fact, each angle on this figure is different. That will lead us down a bunny trail that we might explore at another time. The point here being, if we unravel this hexagon, as we did the dodecagon, and line up the triangles, you'll see they are no longer a series of isosceles triangles. They're not very easy to work with. In fact, we can show that only 3 of these have the same apothem, and the other 3 have different heights. You may think that these 4 have the same height, but using a straight edge, I will show the difference is subtle. But lining it up with the vertex of these 3, we show that the 4th one protrudes. In fact, a numerical calculation will give us the same result. And of course, the 2 triangles on the end have a height that far exceeds these ones. My main point here being that because the polygon is not regular, we do not have a constant apothem, and therefore we cannot apply this area formula to a polygon that is irregular in general. Moving from 6-sided polygons to 4-sided, we can see that a square, being regular in that all the side lengths are the same and all the angles are the same, makes it friendly to be used by this area expression. As we can see by unraveling the square, into 4 isosceles triangles that are equal to each other and verifying with a straight edge that they all have the same apothem. But how about a rectangle? A rectangle has 4 angles that are all equal to each other, that is 90 degrees, but its side lengths are not equal to each other. Therefore, a rectangle is not a regular polygon. So what happens when we unravel it? Not surprisingly, by applying a straight edge, we see that 3 of the triangles have the same apothem, but the 4th one is going to give us some problems. So by the example of the hexagon and now the rectangle, we see that 3 seems to be the limiting number of interior triangles we can make to have the same apothem. Well, that's good news for our analysis of the incircle. If you can see that I've drawn the incircle inside this triangle, and when I unravel it, I find that all 3 triangles have the same apothem. And in fact, that apothem is equal to the radius of the incircle, as I've drawn here. Now, of course, this is an acute scalene triangle, and I've only demonstrated this for a particular case. I encourage you to explore what would happen with other triangles, whether they be obtuse, right, scalene, equilateral, etc. You should find that it doesn't really matter. In terms of drawing the incircle, the radius is equal to the apothem, and therefore we can apply this area formula. Stay tuned to see some further implications of this result. We have already established in another lesson that the radius of a triangle's incircle is equal to the square root of s minus a times s minus b times s minus c divided by s, where a, b, and c represent side lengths and s is half the perimeter. I've just summarized that result in the first line. We have also seen that the area of any triangle or any regular polygon is equal to 1/2 the apothem times the perimeter. In the case of a triangle, the apothem and incircle radius are one and the same, so I've made the appropriate substitution. Next, I distributed the 1/2 to the perimeter, which gives us s. Another substitution and simplification gives us an expression for the area of a triangle using only its side lengths. This is known as Heron's formula. Buckle your seatbelts for a bit of algebra. Starting with the definition of s, I've shown below what each quantity, s minus a, s minus b, and s minus c is equal to. Substitute those into our previous formula for area. Notice that 2 times 2 times 2 times 2 is equal to 16, and the square root of 16 is equal to 4. So I've simply factored a 1/4 out in front of the radical. Follow the color coordination to see how I've reordered the terms and added parentheses. Using the fact that x minus y times x plus y is equal to x squared minus y squared, I've rewritten the previous line as a difference of squares. Then I FOILed it out, rewrote the terms in another order, and expressed my final result as the difference of squares. Pause the video and take as long as you need to absorb this all. In a moment, we will see how this connects to the law of cosines. The area of a triangle is 1/2 the base times height, where h equals a sine theta. To simplify, area equals 1/2 a times b times sine theta. Applying the law of cosines to the same triangle and rearranging terms, I find that cosine theta is equal to a squared plus b squared minus c squared divided by 2ab. To connect my expression for area to the previous result, I need to convert cosine theta to sine theta. This is done using the Pythagorean identity and carrying out the algebra. Notice in the last line I've divided 4a squared b squared by itself to represent 1. This is to make a common denominator between the two fractions. Initially I solved for sine squared of theta so I didn't have to keep writing a radical symbol at each step. So now I take the square root of both sides. Notice the square root of a fraction can be rewritten as the square root of the numerator divided by the square root of the denominator separately. This leaves me with sine theta is equal to 1/2ab times the square root of 4a squared b squared minus the quantity a squared plus b squared minus c squared, all squared. Hold that thought. We'll plug this into the next step. Returning to our expression for area and substituting sine theta from above, we get the following result. Notice that AB cancels with its reciprocal, 1/AB, and 1/2 times 1/2 is equal to 1/4. But wait a minute, this is the same expression we got from here. So by backtracking to where we started, we can conclude that the area is equal to the square root of s times s minus a times s minus b times s minus c. In summary, That is the connection between Heron's formula and the law of cosines. So just as the circumcenter is related to the law of sines, the incenter is related to the law of cosines. Here is an overview of the entire derivation that we just went through piece by piece. Take as long as you need to thoroughly understand how we arrived at this result.